Okay, so we're going to take a look at a little bit of information with solubility equilibrium. And so in the first question, it asks what is the molar solubility for copper carbonate at equilibrium with a KSP value of 2.5 times 10 to the negative 10th. So one thing that we need to make sure that we are aware of is what molar solubility represents. So molar solubility is how much of this compound, okay, so how much dissolves in water. So even those things that are going to be insoluble are going to dissolve a small amount. So when it comes to these KSP equations and calculations, there's a couple of things that you're going to want to know. So we take a look at a sticky here. Make that a little bit bigger. We know that the KSP value or the expression only includes the ions. So no solid. So that's going to be the first thing that we want to take a look at. So if we go back to what's happening here, this solid, so CuCO3 solid in water is going to form equilibrium, and a very small amount of it will dissolve, but in water we're going to have Cu2 plus aqueous plus CO3 2 minus aqueous. And so this is the equilibrium situation. When we go to do this, we want to let X represent our ion. So that's the other important thing. So we're going to let X represent one ion that dissociates. Okay. So if we have one ion then, only, that's going to equal X. If we have two ions, then that's going to be a 2x, and if we have 3 ions, that's going to be a 3x. Okay, so now knowing all of that, we can go ahead and go back and write our equilibrium expression. In this case, KSP is going to be equal to the concentration of copper ions times the concentration of carbonate ions. The standard way to write this is always that those ions are going to be the product because we are dissolving this particular compound. So if each ion is represented by X, then what I can do is I can replace these both with X. So I'm going to replace the copper ion with X. It's one ion because it breaks apart into only one ion. So if we go back up and we take a look at the coefficients, it's only one. And then I'm going to replace carbonate with an X as well. I'm going to then plug in my value for KSP, so that's 2.5 times 10 to the negative 10th. And so X times X actually equals X squared, and I can go ahead and solve for X. So X is going to be equal to the square root of 2.5 times 10 to the negative 10th. And so we can plug that into our calculator. So I'm going to hit my square root button. Oops. Oh. Sorry, I was on the wrong thing. So square root. Oops. Clear. Second square root. There we go. Square root of 2.5 times 10 to the negative 10th. and I get 1.58. I start with 2 sig figs, so I want to end with 2 sig figs. So that means that x is going to be equal to 1.6 times 10 to the negative fifth. And this is a concentration, so this is molar. And that is my answer for this first one. Okay, let's take a look at the next one. So in the second one, it says, what is the magnesium ion and hydroxide ion concentration for a saturated solution of magnesium hydroxide at equilibrium with a KSP value of 5.6 times 10 to the negative 12? So we are looking for, in this particular one, the magnesium and hydrogen ion concentrations. So we're not looking for molar solubility. We will solve for solubility first, though. So I'm going to write that here. To solve, calculate molar solubility first. Okay. And then we'll determine what ion concentration is from there. So I'm going to start off with my magnesium hydroxide, MgOH2, and that's our solid. And so we're going to dissociate that into 1 magnesium ion and then 2 hydroxide ions, 2 OH minus. So now we can write our KSP. So we're going to do our equilibrium expression for this. So KSP is equal to the concentration of magnesium ions times the concentration of hydroxide ions. And because we have this value right here, okay, for the 2 in front for the coefficient, we need to make sure that we square that hydroxide. So don't forget to do that little bit there. Now we're going to go ahead and replace these ions, okay, and make them equal to the actual KSP. So our KSP was 5.6 times 10 to the negative 12. Very small numbers for these ones. And so magnesium is going to be equal to X, and hydroxide is equal to 2X, but we also have to make sure that we still put that squared there. And if I put X times 2X squared, so 2 squared is going to be 4, and X squared times X is going to be X cubed. And so this is going to give me 4X cubed. All right. So now to get this by itself, to get X by itself, we're going to have to divide both sides by 4. So X cubed is equal to 5.6 times 10 to the negative 12 divided by 4. And in order to get this by itself, for x, we're going to have to take the cubed root of each side. So why don't we go ahead and do that? So I'm going to take the cubed root of both sides. And so x is going to be equal to the cubed root of this here. So let's plug that in. So we're going to do 5.6 times 10 to the negative 12th. We're going to divide that by 4, and I hit enter, and that's what I get for inside there. Now I need to take the cubed root. So in order to do that, I have to hit the math button and the cubed root. It depends upon which calculator you have on how to do that. And then I'm going to go ahead and put second answer. And I get this really small number. So x is equal to 1.1 times 10 to the negative 4th. Okay, that is our molar solubility. That is not the answer yet. So that means that we need to go back and take a look at what each one of these would be. So magnesium is equal to X, and so that means that the concentration of magnesium ions is also equivalent to this. So this is equal to the concentration of magnesium ions. But in the case of hydroxide ions, so hydroxide ions are equal to 2 times that number, so 2x, which is 2 times 1.1 times 10 to the negative 4th. And I've actually already done that calculation, and so that is going to be equal to, or you can do it pretty quickly, that's equal to 2.2 times 10 to the negative 4th. And I guess I should put molar in there, put molar in here as well. So those are our answers down here. Okay, these ones are our answers down below here. All right. So now in the very last one, we are asked if a precipitate will form. And so this is when we have to do some comparison. So let's do another sticky note here for some important information that we need in order to do this. So we'll do another sticky, make that green. Okay. All right. So with this, we need to know that QSP, which is what we call the reaction quotient, okay, so QSP is what we call the reaction quotient. It is KSP not at equilibrium, or we don't know if it's at equilibrium. And so we know if QSP is less than KSP, then there is no precipitate. If QSP is equal to KSP, then we are at equilibrium. And if QSP is greater than KSP, then a precipitate will form. So precipitate formed. Okay, so we have to calculate those values and then compare them. So we'd set this up the same way. Okay, so we're going to use our PbCl2 solid, and that breaks apart into Pb2 plus and 2 Cl minuses. We are given those concentrations, so in order to determine what QSP is, it's going to be the concentration of the lead ions times the concentration of the chloride ions squared. We don't need to put X's in there because we actually have the values for those, and so we're just going to plug the values in. Oops. That look a little clearer. QSP. So we have 0.0200 times 0.0100, and we need to square that one. Make sure in your order of operations you do that properly. So I'm going to go ahead and do that first. So 0.01 squared, and then I will multiply that times 0.02, and we get a value of 2 times 10 to the negative 6th. So 2.00 times 10 to the negative 6th. Okay. Is that greater than or less than the actual, so we see our actual value is right up here, and so we can evaluate that. So QSP is 2 times 10 to the negative 6th, and KSP is 1.7 times 10 to the negative 5th. It just so happens that this is less than, the QSP is less than the KSP. And so because of that, no precipitate forms. Okay, so this is a situation right here where QSP is less than, and so there's no precipitate. Okay, so that's it.